Good morning. So we will continue our discussion on successive substitution. As you may recall, we are trying to now work on successive substitution for a two component system. The specific system we have in mind is the fan duct system. So the equations for the duct and fan are given. So I have already dictated this problem to you. So there are two variables in this problem. One is P, which is the head, which is in, or the pressure, which is in Pascal. So the other one is the volumetric flow rate, which is in meter cube per second. So these two are interlinked by the two respective equations. Now we want to solve and get the operating point. I do not want you to see, from your previous knowledge you can try to substitute for Q and solve as a one variable problem and make it make the whole thing very trivial, but that is possible. It is possible for you to do this because it is just a two equation problem. In principle, it is possible to keep on substituting back into the respective equations such that you finally end up with one equation, but that is not the intent. I mean, it is not that somehow we will solve the problem, that is not the goal. We want to see how optimally we solve the problem given a multi component system. That is why it is important for you to recognize that you have to essentially solve this as a two variable problem, right. So the qualitatively how the characteristics will look like are shown in the blackboard. So one is the duct characteristics, where is basically the pressure rise, which is q into 1 to the power q to the power of 1.8. This 1.8 is a consequence of the Darcy-Weisbach equation, which gives you the head loss FL V squared by 2 GD. F itself is 0.182 Reynolds the power minus 0.2. The 2 and minus 0.2 they combine to give 1.8. I have already discussed this in the last class. The fan curve will essentially go like this, right. The pressure and the discharge will be related by this, right. So if you want lot of discharge, then you cannot have high pressure rise which is accomplished, but if you want a high pressure rise, then you have to compromise for a lower discharge, okay, because there is a finiteness to the capacity of the pump, alright. Now we want to find out where these two curves intersect. In fact, they intersect at the point A. What are the coordinates of the point A, right. So we can use the information flow diagram. We first draw the information flow diagram. So this is the duct. It is possible for you to use Q as the input and get P as the output, and for the fan give the P as the input and get Q as the output, okay. This is A. So you can qualify, it is not the information flow diagram, it is an information flow diagram, because there is no law which forbids you from rewriting this equation as Q equal to P minus 79 divided by 10 to the power of 7 whole to the power of 0.55, okay. So this is an information flow diagram. Now let us try to solve this problem with this information flow diagram, in order that all of us proceed along similar lines. I have also given you the starting point. You can either start with P equal to 200, correct, Q is equal to 10 meter cube per second, or P equal to 200 Pascal, alright. How many of you already finished? Is there anybody who has already finished? Why don't you start making the table, right. So I told you, please employ an appropriate stopping criterion. Let this be there. So serial number P of I Pascal sorry what will be the stopping criterion? Huh? But the units are different, right? Is it okay? Okay, we will start with this. Let us say if it is like normalize and then do what? So that's all that looks. Or you normalize and have a separate criterion, each of which has to be less than 0.1% or something. So nobody will tell you what the appropriate stopping criterion is. It is for you to figure out. So whatever is appropriate, whatever you deem fit, you use, right? But it will be reasonable. You should be able to convince somebody that this is adequate. There is no need to proceed with more number of iterations, right? So let us start with this information flow diagram. So should we start with 200? Okay. So we are starting from the fan equation, right? So we are starting here. So it is 200. And you can substitute here, you can get the value of Q. What are you getting? 12.08, that's okay. So with Qi you are getting Pi plus 1. Huh? I think it will diverge, right? Is it diverging?
Yes.
Okay, 1037. Now there is no need to put this additional column, right? Is it required? Anyway, we are going to use this again, right? Or you want this? Now I can start with 1037 here, right? 1027, okay. So I will cancel this. It's not required. Yeah, it will give some. Now from 1027 if you want to go to Qi minus it's gone. Okay, so doesn't work. So we are forced to use the other information flow diagram, right? And then we will see whether it works. If it works, then we will turn around and find out why this information flow diagram did not work. Correct? Okay. Of course, you can realize that there is a q to the power 1.8, there is a p to the power 2 and so on. So it is not linear. So it is non-linear, and apart from this power you also have minus sign and all that. When something is 15 minus something whole square, it is very dangerous, right? There is every possibility that it can turn negative, but you know that both p and q have to be non-negative variables, right? So you cannot have a negative flow rate in this case and all that, right? So therefore it is meaningless to have negative numbers, negative values. So the solution is diverged. So let us go to the B. Yeah, now tell me. I will use for the duct P is the input, for the fan I will use Q as the input, is it okay? Please correct me if I made some algebraical errors, is it okay? Now try, I will give you 10 minutes, please try, it will work. Okay, now you have to draw the tabular column again. Yeah, we start with 200 again. So what is Q? Huh? 3.8. PI?
394.4.
So we didn't calculate QI plus 1, so we will wait, right? Or you can put one more column QI, we can't calculate this now, right? You have not seen the change in both the variables. Let us hang on. So now let us put 394.6. Okay. That doesn't matter, it will convert. Now with 394.6 you can 6.43 you calculated. Now what is this? Please calculate that. Yeah, don't be lazy, I mean, so. Huh? 1 second. The error is 344?
No, that is the next one.
Huh?
37,500.
Oh, too much, man. Ah. Yeah, go ahead, you have a doubt. Ah.
Instead of the var q is we had p, right?
Ah.
So we have changed that and we have changed the equation, starting equation.
Yeah, doesn't matter. No, why do you always suppose somebody says P is equal to, that's what I have been saying, when somebody says P is equal to 79 plus 10.7, why do you always think that this equation should be used to find out P given Q? Who told you that? I never told you that. It is not like a teacher saying that y is equal to mx plus c, x is the independent variable, y is the dependent variable, both are both P and Q are variables in the problem, there is no teacher in life. So there are two variables, two equations are given, somewhere you have to start. Okay. So we started and we cupped, no, last time. Huh? You go ahead, there is a problem with one of the two equations. That is because the derivatives are growing rapidly, that we will see. whenever you try to solve for g of x equal to 0, when x equal to alpha, g dash of alpha must be less than 1, that is a condition, I am going to state that. Okay. So, if the derivatives are derivatives lead to very high values, then the scheme will become unstable. Okay. So, now 6.43, Vikram, you are working on this or?
I got it. 345.
345. We are almost there. Okay. Yeah, we have to wait. Now you should tell me this. Now we have all the values. Please tell me this. I want all of you to get this, right? Quizzes, I will have problems of this level, right, or more, not lower than this. I will not give you a single component system, it will be a 2 component system, you have to do simultaneous. I may ask you to do either this or the Newton-Raphson method, which I will teach you tomorrow. So, we will start with Newton-Raphson method for a single variable tomorrow's class, and you remember that electrically heated filament or some electrically heated wire, that problem we will solve by Newton-Raphson method, and we will solve the same problem by Newton-Raphson method.
2440.7.
2440, not bad, right? Okay, but we are still way off from our target. I think we are almost there. Now you tell me, Abhishek, tell me.
Norm should have a square root.
Don't need. You can take the root of whole thing and say it is norm. It is called the L2 norm. It is always a square. It's a square. If the square root, it is called RMS. It is called a norm. Norm will always have a square. You can go for the 4th power also if you want. I have no problem. But 4th power means it will be, you have to take the appropriate stopping criterion. Yeah. Error is coming down rapidly. 124. Oh. Yeah. Go ahead. Point
7. 5.96.
See the way it is rapidly converging. If it converges, the successive substitution will rapidly converge. If it diverges, it will rapidly diverge. Success or failure is guaranteed, immediate. It does not agonize. It does not agonize you. Yeah, what is the value now? I think we have got down, we got to some decent values. 7 point? Okay. Now proceed. I think I put one more. $354.3. Okay. We'll put 354.3 here.
5.966667.
No, I'll put 5.97. We are there almost. What is this guy? 10 to the minus?
0.36.
It's still 0.36. Yeah, one more then. With 5.97.
54.2.
0.2. Time to stop, huh? Point? So we should have some realistic expectation. If you put 10 to the power of minus 8 and you should not commit suicide. I mean, you put 10 to the power of minus 8, it won't, okay, otherwise you should program it and you should not round off to the second decimal and have 10 to the power of minus 6, right? You start writing up to the 4th decimal and then you have 10 to the power of minus 4 or minus 5. When you are rounding off to the second decimal, 5.9697, it will always have 0.01 error and all that. So you should understand the importance of, I mean, the number of digits, significant numbers and significant digits and all that, right? When you say the error associated, when you say the temperature is 36.54, when you say the temperature is 36.5 degrees C or the temperature is 36.50 degrees C, there is a difference. When you say if the temperature is 36.50 degrees C, you are declaring that you know for sure that the second decimal place is also 0. That means you have an instrument which can resolve that. Therefore, when you are having an instrument which can resolve only 0.1 degree centigrade, you are taking the temperature measurements repeatedly. Once you get 36.5, once you get 36.4, once you get 36.2 and all that, and you take 10 or 15 readings and average, we should not write the average as 36.546. The instrument cannot measure that. The average may be a number which has got 3 decimal places, but common sense tells you that you have to round it off to the value which is normally shown by that thermometer. So this is engineering, right? There is no, just because your calculator gives 4 numbers, you should not put 4 numbers. 36.5454, if you want to design a thermometer which will be so exact, you will get PhD. So that is you cannot design. Alright, okay, so that is the importance of. Now okay, this information flow diagram works, so we are happy, we can go home, not yet, 27 more minutes. So, but now we will have to figure out why one information flow diagram works and why one information flow diagram does not work. Apart from silly things like whether I take the wrong information flow diagram in the quiz or exam, or let us leave all that, okay. Even in this case, even if you go to the incorrect information flow diagram, in the sense that you go to the information flow diagram which does not converge, you know that immediately within 2 iterations it does not converge, you will go back, so the wastage is only 5 minutes, okay. Now let us examine from a numerical point of view why that the other information flow diagram did not work. So everybody is through with this, okay. So what did we call it, information flow diagram A or 1? Okay. So if you are trying to get the roots of the equation x equal to 0 around x equal to alpha, the goal is basically g of alpha must go to 0, right? You want it to go to 0, right? Then alpha is a root, I say it is approximately 0, I mean it will not be 0.000, you know that within limits it is all right. So the requirement now is I can do a Taylor series expansion and then take an example and show you why when g dash of alpha is greater than 0 the whole thing will diverge, but this is not a course in numerical methods. Even so, for the sake of completeness, I am just trying to give you an idea of some people who are perplexed and some people who are bamboozled as to why one information flow diagram is working, the other is not, basically because the culprit is because of the nonlinear powers. Now we will go back and see for the information flow diagram A, for the chosen initial condition where the derivative is indeed greater than 1, shall we do that? Let us do a quick exercise for 5 minutes, and then in the meantime I will put these numbers on Microsoft Excel and I will show you the operating point on Excel. While I work with this, you guys will work with that, right? Take the information flow diagram A and get dou R by not dou P by dou Q and dou Q by dou P at the initial guess whether it is 200 or 10 meter cube per second, and see whether you are able to get it. Let it be there. Did it go up to 1000? That is very dangerous, no? Oh. I put some numbers which are reasonable. These were the equations we used. Second case. Okay, so this is what is this now? Q. This is Q, correct? This P, yeah, correct? Okay, now I will. So this is Q, this is P. Okay, so is it 0.5555? What is it? Too many fives, huh? Okay. So the numbers are decent. Formula is correct? Is it correct? Okay. 15 minus A1, huh? Is it correct? Okay, now what's the big deal? Okay, I plotted the two equations. How do I solve the, how do I show it now? I should use again this equation. From A1 I should be able to get the P, right? From A1 I should be able to get the Q. What is A1 is? P.
Q.
Huh? Tell me what is A1 is? A1 is Q, okay, and B1 is P, huh? Now I should be able to get P from A1, that is starting from Q, okay. So using the, which equation did we use here? Okay, from the other equation I have to rewrite, or what was the other equation? So P equal to 10.7, okay. All right. What happened? Page special, huh? Come, tell me, Abhishek. Page special, huh? Done?
Okay.
Okay. Now, what is this? This space is all right. let us do. So there we go. Okay. Should we make it bigger? Okay. Always dicey, huh? Okay, so where are these insert shapes and all that, man? Huh? Not picture. Where are the arrows? What is that? Text box. I think I will die finishing this. Okay, this is so this is basically the operating point. So this is basically P, correct? X axis is P. This is Q in meter cube per second. This is your P. Okay. I want to call somebody who is good in Microsoft Excel. I want somebody to do one exercise live now, okay. That is the duct characteristics are the same, but suppose the fan characteristics are displaced 10% above and 10% below, the operating point will be shifted. So can we take this equation, the equation given in blue, suppose you want to multiply by a factor of 0.9 or a factor of 1.1, then graphically depict how the operating point changes. Who is going to volunteer? Can we draw two more curves? Can we draw two more curves on this?
Yes.
With the same value of with the same x-axis values. I want to generate two more fan curves for the same duct curve, and they are related to the original fan curve. Are you getting the point? This curve, if it gets shifted here, what happens to the operating point? We know that it goes up. Just graphically seeing that. Can somebody do it, or we'll just give up and go to the next problem? Give up. Okay, that's good. That's the spirit. Okay, so this is how you do it on. This is how you do it on Microsoft Excel. There is no need to save the work. We can always generate the work. Okay, so more than 2 variables, it's difficult to show. Okay, you are supposed to answer one question. What happens with G dash of alpha? Okay. So this is the solution to the problem. So people who have completed this, let us do the last part of the problem. Examine the stability, examine the stability of the system at the operating point. This was problem number 6, right? Problem number 6, whatever you have done so far, take it as part A. Part B, examine the stability of the system at its operating point. Examine the stability of the system at its operating point. What do I mean by that? So if I start with an initial guess which is close to the correct answer, but which can be left of the correct answer or right of the correct answer, whether it is proceeding to the same operating point, that you will have to numerically test. That means you have to go back to the same equations and see whether you overshoot. Are you getting the point? If you overshoot, suppose you start with, you go to 360, when you go to 360 after 1 or 2 iteration, does it come to 354 and 5.97? That is one way of checking it. The other is instead of you approach from 5.99 5.96, so you approach from 5.8 or 5.6 whether it goes, just complete this, do this exercise so that this solution is complete. How to determine the operating point of a system using the method of successive substitution? How do we show this graphically? Why one information flow diagram is not working? Because of the first derivative, and then how to examine the stability of the system at its operating point. Yeah, but now for the sake of completeness we finish it. I know that we have started from 3.8 and but I want you to specifically examine very close to that. Instead of 5.97 you can start with 5.85 or something and go to 6.15. If you start with 5.85 and 6.15, are you quickly coming back to 5.97, or you start from 340, you also start from 360, whether you are quickly coming back to 354.2. Show it, it will just take 5 minutes so that the notes is also complete, so that your understanding is complete. And then we will go to one more problem, that will be the last problem on successive substitution, and tomorrow we will complete that and start the Newton-Raphson method. Please complete this. So I will write the question on the board. So that we still get the same answer. Done? Okay. Yes, Deepak. P of x equal to?
The differentiation. What exactly to do?
No, you will. What is the other information flow diagram? Okay, let us finish this. It is also being recorded. So you are okay with this space? I feel that we are going a little slow, but it is okay. Okay, as people are examining, we will also try to answer the other question. Why this information flow diagram, for example, works. So what is your dou P by dou Q or dP dQ, right? So you just say 15 into -1, right? That is it. Into that that is there into which is multiplied, yeah, is this coming? Please evaluate this. then huh? Yeah, you have to take q at the initial starting 26, okay, let us see. Then dq by dp, there should be only one value for this. Second one is
017.
So the first one, Q you take it as 10 or you take Q as 3.8? You assume the initial conditions you have given or?
no, initial condition is what did we assume starting point? If you use p is equal to 300, then this q must be equal to that whatever you get from that. Yeah, one of the two initial conditions you have to use. Okay. Now if you do this, what are you getting? The other one is 0.01. Okay. So one of the derivatives is very small compared to one, it will not grow. The other one is trying to create some mischief, but eventually after a few iterations they will reach some balance. But if you look at the other information flow diagram, I think you get very large values for both the derivatives. I got some 119.8 or something. Okay, it's very high values. So that is, this is not an exact mathematical justification of why it is not working. This is a, but this gives you an understanding. This gives an approximate understanding of why certain information flow diagrams will not work. As you know, because p and q are continuously changing, with every iteration these things will fluctuate. It is highly non-linear and so on. But one of the derivatives is showing promise. But if you go to values which are closer, but when you are actually reaching the correct answer, after, if you work this derivative out for the third or fourth iterate, both will be less than 1, and that is how we are eventually getting convergence. Okay. But no, one was 119.8 or something.
One is very big.
Yeah, but what I am telling you is you have to do this for each of the iterations and see how it is progressing, right? So the previous information flow diagram, when it is diverging, if you look at the derivative, it will be enormous. That is why it is diverging. But here, though first one of the two derivatives was more than 1, the subsequent derivatives, it will die down, it will settle down. Okay.
Here Rajan, if you write the equation like this, you have the error there, and the error is getting, it's not growing.
Yeah, because
the
you have put into
the error is going.
Yeah. See, actually, already there is a already we screwed the system by not allowing the errors to propagate, because you are raising something to the power of 0.5. When you raise something to the power of 1.8 or 2, I mean mischief is guaranteed, unless you are so smart that you start at 354, you start at 354 Pascal and 5.97 meter cube per second, then you can use, I do not know whether the other information flow diagram works when you start very close to the initial, when you start very close to the true value, right. So that is why, so this is a good exercise in the sense that it tells you how to rewrite the governing equations in such a way that even when you are way off from the final answer, because you are raising something to the power of 0.55, so there is, it constrains or it bounds the errors. Are you getting the point? So you can work out, you can qi and qi plus 1 and delta q, I mean the error, how it propagates, you can write it mathematically, and this is why this information flow diagram works, whereas the other information flow diagram does not. Okay. So it is already 10:57, we will close. Tomorrow we will solve another interesting problem. A truck is going up the hill. So again there are two characteristics, there is a load characteristic, the other one is the engine characteristic. So these two have to meet and you have to get the operating point of the truck. So we will solve this using successive substitution and proceed to Newton-Raphson method.